In this video, we're going to take a look and see how the second derivative can be used to try to help us identify where a relative maximum and relative minimum might be, or where they are. So let f be a function such that the first derivative at c is 0. Right? So we're telling you that it is a critical number, right? C is a critical number. And the second derivative exists, right? So we are requiring that the second derivative exists on some interval that contains c. If the second derivative at c is equal to 0, then what does that tell you? Well, right there at c, our second derivative is greater than 0, so that means it's curved up right at that point. So right at that point, we must be at the bottom of a valley. So it has a relative minimum at that point. On the other hand, if our second derivative is negative at c, so right at c, it's negative, so it's curved down. Oh, so if that happens, we must be right at the top of a mountain. So we're at a relative max. So if our second derivative is equal to 0, then this test fails. And so it could have a relative maximum or a relative minimum, or it could be neither at that point. In those cases, you would use the first derivative test. The first derivative test, that's where you're looking to see if to the left of it, is the function increasing or decreasing? To the right, is it increasing or decreasing? And then making your determination based on that. So here, we only need to know what is happening exactly at the point c. So at c, the derivative is 0. At c, the second derivative is positive. We can tell you it's a minimum. If at c it's 0, the derivative is 0, and the second derivative is negative, we could tell you with certainty we're at a maximum. All right, so let's look at an example. So let's find the relative extrema of this function. So f of x is negative x cubed plus 7x squared minus 15x. So we will first find our derivative, f prime of x is negative 3x squared plus 14x minus 15. So we have this. Now we need to find our critical numbers. So let's find the critical numbers. So f prime of x equals 0. How does that factor? I don't see it immediately how that factors. Maybe you do. But since I don't see that immediately, I might use the quadratic formula here. And so x is going to be negative 14 plus or minus square root of 14 squared minus 4 times negative 3 times negative 15 all over 2 times negative 3. And if we do that, we get negative 14 plus or minus the square root of 16 over negative 6. And so x is 5/3, or x is 3. So what does that tell us? Well, these are the possible locations of maximums or mins. And so now what do we want to do? Well, you might say, I just want to do the first derivative test. I'm going to do a sign chart for the first derivative, find out what's true to the left of that point, to the right of the point, 5/3. Does it change from increasing to decreasing? What's happening on either side of 3? Instead of doing that, though, let's look and use our second derivative test. Right? So we're going to use the second derivative test, and so you might imagine, yeah, we should take the second derivative. Our second derivative is negative 6x plus 14. Now, what are we going to do with that second derivative? Now, you're probably, some of you might be tempted to set this equal to 0. And if we were trying to find out about concavity, that's exactly what we would do. But here, we're not trying to find out about concavity on either side, like intervals of concavity. We will only want to know what is true of the concavity at these 2 points. What is true of the concavity exactly at this point? Is it concave up or down? What's it true exactly at this point? So we are going to take and plug into our second derivative 5/3. So -6 times 5/3 plus 14. When we plug that in, we are going to get, I guess +4, which is bigger than 0. So what is going to happen at 5/3? Well, we have a minimum at 5/3. Our first derivative was 0, and our second derivative was positive, so it was curved up right at that point. So we are at the bottom of a valley. We're also going to plug in 3 into our second derivative. When we do that, we will have -4, which is less than 0. So it tells us right at this point it is curved down. So we must be at a maximum when x is equal to 3. And those are the locations of the relative maximum and relative minimum. Come back for our next video and we will look at 2 more examples of this. We will see you there.